Hello and welcome. Today we're going to be talking about L'Hopital's rule on indeterminate forms other than the 0 over 0 and infinity over infinity conditions. So recall L'Hopital's rule, which states that if limit x goes to some point a of a function f of x over g of x, if you have a ratio of two functions, and limit of x goes to a of f of x is equal to 0 or infinity, plus or minus, okay? And we have limit x goes to a of g of x is equal to 0 or plus or minus infinity, such that you have a 0 over 0 type situation or a infinity over infinity type situation, then your limit f of x over g of x, limit x going to a, can be re-expressed as a ratio of the derivatives. All right, and this hopefully, the idea here is that hopefully this is simpler. And in previous lectures, of course, you've probably seen that this does work quite well to simplify a great many limit problems. All right, so now what we want to talk about today are other indeterminate forms. Okay, and there are several. The first is what we'll call the 0 times infinity case. There's another one, and I'll put these in quotes because these aren't really mathematical expressions because they make no sense, but rather they invoke the idea of the process of two things diverging in different ways. We also have the infinity minus infinity tug-of-war situation. Another one is all the different exponent ones. So we have 0 to the 0. We have 1 to the infinity. And we also have infinity to the 1. Oops. Sorry, I got to bring that back up. About that, the tablet I used had a little problem. I've got it fixed now. And we have an infinity to the 1 case as well. All right, in all of these, what we're going to do is we're going to use algebra to modify the expressions into a L'Hopital's rule acceptable form of either 0 over 0 or did it again. An acceptable form of 0 over 0 or infinity over infinity. Okay, so let's just give an example of how this works. All right, so the first example we'll talk about is a really straightforward one, which is going to be a 0 times infinity situation. Okay. So we're going to look at the problem. Limit as x goes to 0 from the positive side of x times natural log of x. All right, so this is a situation where limit of x, where x goes to 0 from the positive side, that's going to go to 0. And the limit of x goes to 0 from the positive side of natural log of x goes to negative infinity. So this is clearly a negative, an infinity times 0 situation. But what we're going to do is now modify this by doing a slight change to the algebra or to the expression. Natural log is going to stay where it is, but now we're going to take the function x and make it a ratio 1 over x in the denominator. Now, in this situation, what we have here is actually a infinity over infinity case now, which we can use L'Hopital's rule on. So L'Hopital's rule can be used, and we can take the limit now of 1 over x all over 1 over x, negative 1 over x squared. Now we have to simplify, and this is clearly going to be negative x after we do the simplification, and the answer is 0. So we were able to compute this one fairly straightforwardly using L'Hopital's rule, but we had to do an algebraic trick in order to get it into a infinity over infinity form in order to make it work. All right, now I'm going to talk about another one. We're going to talk about this one, the Tug-of-War problem of infinity minus infinity. All right, so let's give a few examples of this one. We're going to look at this example: limit of x going to pi over 2 from the negative side of secant of x minus tangent of x. Okay, in both cases, so limit of x going to pi over 2 from the negative side of secant of x, which one is that going to be? That's going to go to infinity. And limit of x going to pi over 2 from the negative side of tangent of x is also going to go to infinity. So that's coming from the negative side. All right, in order to appreciate what this is, so we need to now, what we need to do is actually take this expression and we need to rationalize it. We need to make it a ratio. In this case, we have to do this, so we have to look at secant and recognize that it's actually 1 over cosine of x, and note that tangent of x is actually sine of x over cosine of x. So they have the same denominators already. Therefore, we can take x going to pi halves from the negative side and combine these together to get 1 minus sine of x all over cosine of x. All right. And now this is going to be in a form of a 0 over 0 situation. So we can use L'Hopital's rule on this particular one. Coming from the negative side of pi over 2, now we can take the derivative of the top, we're going to get a negative cosine of x all over a negative sine of x, and that's going to lead us to a 1 over 0, which is equal to 0. So we're able to compute that limit once we got it massaged a bit. All right, let's try again. Do another one. Let's take the limit. Let's take the limit of this function. Limit of x goes to 0. So no, x goes to infinity of 1 plus 1 over x to the x power. All right, so if I look at 1 plus 1 over x, that's going to go towards 1 as x goes to infinity, right? Also note that, of course, x is just going to go to infinity. So taken together, this is a 1 to the infinity situation. Okay, so how do we transform this problem? What we're going to do is actually, we're going to transform it. We're going to transform by taking the log. Okay, so if I take the natural log of 1 plus 1 over x, quantity x, note that, again, I'm taking the limit as x goes to infinity here, right? But what I need to remember then is that natural log is continuous. It's continuous on its domain, and that means I can always move the limit inside. And therefore, if I instead compute this limit, all I have to do at the end is exponentiate everything. So basically, compute this, then exponentiate at the end to get the limit in question. Okay, so let's do that. Let's look at this limit. X goes to infinity. Now, we know the law of logs, that x can go out front. We have natural log of 1 plus 1 over x. Okay. So, again, we have a situation where limit of x goes to infinity of natural log of 1 plus 1 over x. That is going to go to 0, okay? And the limit of x goes to infinity, is going to go to infinity. So, taken together, this is a case of 0 times infinity. So what we have to do, of course, is use the transformation that we just explored in the previous problems of now taking natural log of 1 plus 1 over x and dividing it by 1 over x, all right? And now this problem is a 0 over 0 indeterminate form, in which case, I'll move it down here, we can use L'Hopital's rule. Sorry, that's limit going to infinity. X going to infinity. We take 1 over 1 plus 1 over x. That's the derivative of the top. But then we have to use the chain rule to get the inside. We get that, the derivative of 1 over x. And now the derivative of the bottom is going to be negative 1 over x squared as well. That's really nice. These cancel. And to finish up the calculation, we're going to have a 1 over 1 plus 1 over x, and that's clearly going to be equal to 1. All right, so now let's recall the limit of the problem in question is not 1. That is the limit of the log of what we wanted. So what we've actually determined is that this is equal to 1. All right. What we need to do now is exponentiate everything. So what I have to do is exponentiate everything, and I get limit x goes to infinity of 1 plus 1 over x, quantity to the x power, is equal to e to the 1, otherwise known as e. So now we have a limit. In fact, this serves as one of the definitions of the value of e. If you want to approximate e, you simply take this, put it into your calculator, and make x bigger and bigger and bigger and bigger and bigger, and you'll get a fair approximation of E. So that's an interesting one. So we did many examples now of different algebraic transformations to move our indeterminate forms, our alternative indeterminate forms, into the acceptable forms in order to compute L'Hopital's rule. Thank you very much.